So the intermolecular forces are the reason that we have surface tension, viscosity, and capillary action. So we're going to look at those. Those properties result from intermolecular forces. So when we see something like this, a spider web, and it's got dew on it and little droplets of water, why is the water in little spheres? It's intermolecular forces. You can, if you're careful, you can float a paperclip or a needle on the surface of water. Even though it's more dense than the water, you can make it float. And you can see here how the surface of the water seems to be bent, almost like you've got a pool with a pool cover on it and somebody laying on top of the pool cover, right? This is called surface tension. And so the water molecules at the surface hold together and resist being separated. And so this, water bugs that skate on top of the water, that's how they do it, because they're on top of the surface tension. So what is surface tension? It's the tendency of liquids to minimize their surface area. There's a fly, like you might use for fly fishing, and it will float on top of the water because it's sitting on top of the surface tension. Of course, we can quantify surface tension. It's the energy needed to increase the surface area of the water by a specific amount. Water has a surface tension of 72.8 millijoules per square meter. Different liquids have different surface tensions. So if we look at a two-dimensional slice of water, we see that molecules in the interior are going to be attracted to water molecules all around them. So this one might be interacting with 6 different neighbors, whereas this surface molecule is interacting with only 4 neighbors because it's on the edge. It has nobody on this side to interact with. Those interactions lower the potential energy of the water, and so it's trying to get into a place where it has the lowest energy. It's going to do that by minimizing how many molecules are at the surface, because the more molecules you have at the surface, the higher the energy, right? So not so good. So water will minimize its surface area. Another way to think of this is if we're trying to increase the surface area, we're going to have to push some of these aside, and some of these interior molecules are going to have to come out and be on the exterior, on the surface, and have fewer interactions. They're not going to like that, right? It's like, oh, we're all fun in the middle of this party, and now you're trying to get all of us to go out on the edge where we can't talk to as many people. No, we want to be in the middle of it where everything's happening. Yeah. So surface tension is what we observed in that video. This is actually the same guy on the space station. He's a Canadian. It's okay. Giant drop of water. Surface tension makes water try to get into a spherical shape, because that's a geometric shape with the smallest surface area to volume, right? So the smallest surface area is to get into a volume. A sphere. The smallest surface area is to get into a sphere. So surface tension causes water to do that. We don't see big spherical drops of water on Earth because of gravity. If you watch water drop out of a faucet, or, maybe sodium hydroxide dripping out of your burette, right? You see that it hangs in that teardrop shape. It's not sitting as a sphere at the end when it gets to a certain size. It's got kind of a teardrop shape. That's because gravity's pulling down on it. And when it gets big enough, gravity is pulling on it so hard that it breaks loose from the burette tip or the faucet or whatever. But in space, where there's no gravity to pull things down, the water is going to stay together. So on Earth, if we take a wet washcloth and wring it out, the water's going to fall, right? But in space, he did that. You wring out the washcloth. The water has no reason to go down or away. It's going to stay with itself. And so it just spread out around his arms. It's like very crazy. So the surface tension is biggest when the intermolecular forces are strongest. If the intermolecular forces are weak, then the surface tension is going to be weak. Because if we look at this, surface tension you could also think of as the resistance to being penetrated, to push something in here, to get something to go through. You have to disrupt the intermolecular forces on the surface, right? The stronger those intermolecular forces are, the more resistance there is to something going in, right? So water has high surface tension, and so little water skater bugs can skate on water. They can't skate on gasoline or ethanol because those have lower surface tension and they'll just sink. So any questions about surface tension?
It can be broken.
Yes, it can be broken. Surface tension can definitely be broken. And you can also mess up the surface tension. So you could try this at home. I don't know why I've never tried it. No, I do know, because I get home and there's other things to do. If you take a very clean dish and very clean water and a very clean needle, and you're very careful, you can float a needle or a paper clip on the surface of the water. Now, if you add something to that water, a little bit of soap, a little bit of alcohol, that will disturb the surface tension of the water, because now you don't just have water molecules, you have water molecules and soap molecules. And so the surface tension will be less and the needle will sink. That's why the dish has to be really clean. If you've got soap residue on the dish and you put water in there, now you've got soap mixed in with your water, and even just a little bit will cause the needle or the paper clip to sink. Viscosity is another result of intermolecular forces. And whenever I hear the word viscosity, I think of the motor oil commercials. They're talking about viscosity breakdown, right? It's a bad thing, viscosity breakdown. Viscosity is the resistance of a liquid to flow. So you could think of it as how thick the liquid is. We all know that honey pours much more slowly than water does, right? And motor oil, the viscosity of the motor oil is a measure of how easily it flows. You want motor oil to coat the moving parts of your engine. And if it's too viscous, it will be kind of jamming it up. If it's not viscous enough, it'll just run off of the parts and it won't lubricate. And so you have to get this balance in the middle. So viscosity depends on intermolecular forces. So stronger intermolecular forces, greater viscosity, greater resistance to flow, thicker liquid. Here we can look at this table showing again some of the normal hexanes, and we see the molar mass increasing. If we look at their formulas, we see also that the length of the molecule is increasing. And here we can look at the viscosity. It's measured in centipoise. A poise is 1 gram per centimeter second. You don't need to know that. But the viscosity is increasing. So viscosity depends on the molar mass because dispersion forces increase. These longer molecules are going to have more surface area to attract each other. And with these hexanes, because of the rotation around single bonds, these are not like long spaghetti sticks that are uncooked. They're more like cooked spaghetti, and they can tangle up with each other. And so the longer ones can tangle more easily, and therefore they resist flowing. They have higher viscosity. Viscosity also depends on temperature. So, we do pancake syrup or honey? Honey? Okay, so you want to put some honey on a biscuit or something, and it's just like so thick you can't get it to come out, right? So what do? You warm it up. Because when you warm it up, it becomes more watery. It becomes less viscous. Inviscid is the opposite of viscous. So at higher temperatures, what happens is you've got thermal kinetic energy of those particles, right? It's like ANSI students. You guys are getting higher in energy now because you've been sitting here for over an hour. So the particles are moving more. And so they can partially overcome those intermolecular forces. So they're overcoming more of the intermolecular forces, so they're not sticking as well, and so it will flow more easily as the temperature increases. So modern motor oils are really pretty awesome. So there's synthetic and there's just like regular. The synthetic motor oils have polymers in them. And what the polymers do is at low temperatures, they'll coil up and be sort of spherical. And at higher temperatures, they'll straighten out. Well, a long molecule is going to have stronger intermolecular forces than a coiled up one. At higher temperatures, oil, anything, becomes less viscous. And so we want to counteract that. We'd love for our motor oil to have the same viscosity at all temperatures. So by having these polymers in the motor oil, when the engine gets hot, the polymers uncoil, maintaining the viscosity of the oil. And when it cools down and gets cold, they coil up, reducing the viscosity. And so we moderate changes in viscosity. Around here, it's not as big of a deal. Where I grew up in Minnesota and Iowa, where it gets really cold, people in Central California have no idea what really cold is. Really cold is it was below zero for 10, 15 days on end, never got above zero. That's cold. That happens. And people still live there. So there, your motor oil, you may need to use a different motor oil in the winter than you do in the summer. Because the one you use in the summer might just become like glue at minus 20 degrees Fahrenheit. Here we see just water. As we increase the temperature, the viscosity decreases. And then capillary action. Capillary action is the ability of a liquid to flow against gravity up a narrow tube. So here we have a picture of someone getting a blood sample taken. So you prick your finger and some blood comes out in this little tiny capillary tube. You touch it to the blood and the blood just runs up. That's crazy. Things going against gravity, right? It's capillary action. It's a combination of two different forces. There's cohesive forces and adhesive forces. Cohesive forces are the intermolecular forces that are keeping the liquid attracted to itself. The adhesive force is the attraction for those particles, the attraction they have to the glass or whatever the material of the tube is. So adhesive forces are going to cause the water or the liquid to creep up. Cohesive forces are going to cause it to stick together. So if your adhesive forces are stronger, the liquid will go up. If the cohesive forces are stronger, it won't go up, or it will go up less far. Because it will only go up a certain amount because gravity is also opposing. So a narrower tube, the liquid will rise higher. Here's the narrowest one. It's a little hard to see. It's all the way up there. But even a larger diameter, it will go up a little bit. So, if you take a straw from your soda and you pick it up, there's usually a little bit of liquid that stays in there, right? That's the capillary action. This also is what gives rise to the meniscus on the surface of liquid. So here we have an aqueous solution, and this is our familiar meniscus. It almost looks like a contact lens that's sitting on the top there. The water is creeping up the sides of the glass tube as adhesive forces. The cohesive force is what's keeping it together. In mercury, the meniscus goes the opposite direction. It bulges up in the middle instead of dipping down, because mercury's cohesive forces are stronger than its adhesive forces. Mercury is not attracted to the glass like the water is. And so we see a different shape of the meniscus. If you use different materials, the shape of the meniscus may be different. There are certain plastics that will give you a flat, no meniscus, with water, because the force of attraction for them is just balances with the intermolecular forces in water.